We are now going back to students' presentations that are from different groups. So now we have Michelle Fairhurst from the Feelings on Pits group and Pascale Lakey from the Chicago group as a postdoc and as a doctoral student, and they have what is my favorite title of the session, which it is what appears on the surface is not what it seems. Isn't it ironic?
Understanding particles on the surface level is important because they can adversely affect health. They can also impact climate by absorbing and scattering radiation, and they can lead to a reduction in visibility, as shown in this photo of Lake Arrowhead, which shows a haze covering Los Angeles. Atmospheric particle concentrations can be measured using both stationary and mobile labs, such as this NASA DC-8 jet shown here. Modelers can also predict particle concentrations by putting known atmospheric processes into their computer models. However, there are often discrepancies between the concentrations which are measured and those which are predicted by the models, and this is likely to be due to a lack of complexity in the models.
Complexities is how particles grow, which is not yet well understood. But what we do know is that gases emitted from sources such as trees or plants, or industrial sources or vehicular sources, are transformed in the atmosphere to form different gas molecules, which can then interact with existing particles and subsequently grow them. And it's this last growth step that is poorly understood at the moment. But we have some ideas on what might govern this growth step. Could it be particle phase? So down here at the bottom, we have a bunch of different common household items of different consistencies or viscosities, as we like to use. So if you could imagine these different phases representing a different particle, and if we take a marble, which would represent a gas molecule, you could imagine that the gas molecule or the marble would penetrate or be taken up more readily in olive oil, say, rather than peanut butter. Is it solubility? And we've all heard the term that oil and water do not mix. So if the particle's surface and the gas molecules are vastly different, will that uptake not be feasible? Or is it something else? Is there some kind of chemistry that we're lacking in the knowledge? And it's this point here where experimental studies and modeling studies can unveil this mystery. So in our work, we took compounds that are readily found in the atmosphere, reacted them together to form products, and based on the products that we got, can we determine the mechanisms on how we got there? So to do this, you need to know our key players. So our gas phase molecule, or a marble, is an amine, and the reactive group is right there shown in purple. We react it with our solid acid, and this can be indicative of groups found on the surface of a particle. And we have a special term for this kind of acid. It's called a diacid, because the two pairs of reactive red functional groups are linked by a carbon backbone chain, as you see in the gray circles. So we're interested to see that if we vary the length of that chain, will the reactivity depend on whether or not there's an odd or an even number of carbons? So to do this experimentally, we have a custom-built cell that was made here at UCI, where we have our solid acid phase hidden or shielded underneath a lid. And our gas phase amine can come in and fill the cell. And using our instrumentation, we can measure how much amine we have in the cell while the lid is closed. We can then open the lid, thus exposing the amine to the acid. And if a reaction occurs, what the acid is essentially doing is pulling amine molecules out of that cell. So while the lid is open, we will see a decrease in the amount of amine in the cell. And we actually have seen that the magnitude of that dip is much larger when our carbon backbone is odd versus even. So we thought, why are we seeing this difference between odd versus even? So we took a step back and we said, well, what should happen in this gas to solid reaction? So what should be happening, we thought, is that our gas phase amine will encounter the acid on the surface. As the reaction proceeds, we will form a solid surface product layer, or shell, that will essentially stop the reaction. So we thought in both cases, if we're forming this solid product layer, again, why is there this difference between odd versus even backbones? So what's actually happening in our system was surprising. When we have an even number of carbons in that backbone, we get a solid product. But when we have an odd number of carbons in that backbone, we get a viscous liquid. So if you could imagine back to our marble example, representing our amine, you can see that the marble or the amine will be taken up more readily in our viscous liquid than in our solid product. So to gain an insight into what's happening on a molecular level, Pascale did some kinetic modeling for our system.
So we developed a new kinetic model to investigate one of the odd carbon carboxylic acids known as glutaric acid. So this is a schematic of a model, and although I won't go into much detail about it, there are some important processes which are included. These are adsorption and desorption of the amine to the surface of the glutaric acid, solvation of the amine from the surface into the bulk of the glutaric acid, bulk diffusion of all species, and reaction of the amine with the glutaric acid. So we included these reactions, and although the glutaric acid is a solid, the products are liquid, as was shown on the previous slide. So the main point about this next graph is that the model output, which is shown by the black solid line, can fully reproduce the experimental measurements, which are shown by the data points. We can also use the model to explain why the uptake decreases over time, and this is due to a surface depletion of the glutaric acid. The model can also be used to output information which was not directly measured during the experiments, such as viscosity as a function of depth into the glutaric acid and as a function of time. So where the glutaric acid dominates, you get this region of high viscosity, whereas near the surface, where the products start to form, you get a region of low viscosity. So overall, we've shown that for odd carbon carboxylic acids, there's a large uptake and the products are liquid, whereas for even carbon carboxylic acids, the products are solid and there's a small uptake. And we've used a computer model to better understand the processes and reactions controlling this uptake. And in the future, we hope that by including these reactions and processes into atmospheric models, we'll be able to better predict atmospheric particle concentrations and reduce the gap between the models and the measurements. So thank you for your attention.